Next one we look now will be question 37, which we have here. 3 4 ohms resistors connected in parallel have a potential difference of 16 volts applied across them. What is the total current in the circuit? So a very quick solution there. Okay. Have 4 ohms resistors in parallel. I have 16 volts potential difference. Yes, this is 3 4 ohms. Let me just write it in words. So 3 4 ohm resistor in parallel. So to solve this question quickly, we must know where the question is coming from as usual, which is coming from current electricity. So this is coming from current electricity, and you must know how we sum up resistors, whether in parallel or in series. So we have resistors in series. For resistor in series, total summation of the resistance will be equal to the summation of the individual resistance that you have. So R1 plus R2 plus R3 up to the total number of resistors that you have. This is this for series connection, right? And if it is for parallel connection, you're gonna have 1 over R total there equals inverse of everything there, 1 over R1, 1 over R2, 1 over R3, up to the 1 over the total number of resistors that you have. So this is for the parallel connection. So here, since we're given parallel connection, we have 3 of them. The diagram may kind of look like this. Say this is one resistor. Okay, may kind of look like this. Okay, that box for the resistor is connected. Right, you have the third one along the middle. You see, okay, somewhere like that. So each is 4 ohms, 4 ohms, 4 ohms. I have the voltage applied across them. You have that to be 16 volts here. That's the case, 16 volts. Okay. So how do we sum up these resistors in parallel? So we're going to say 1 over R total equals to 1 over, one of inverse of each of them. 1 over 4 plus 1 over 4 plus 1 over 4. So this 1 over 4, there are about 3 of them, so I'm going to say 3 into bracket 1 over 4 is my 1 over R total. So from here, R total equals to the inverse of 3 over 4. That is 4 over 3 ohms, right? And the question is asking for the current, the total current, yes. So that is my R total there, 4 over 3 ohms. So to get the current, we are going to use the Ohm's law that says that voltage or potential difference is proportional to uh, current passing through a conductor. So where we introduce a proportionality sign, which is where we introduce an equality sign, moving a proportionality sign, which is resistance, so Ri or IR. So since the voltage is 16 equals total resistance, there you have 4 over 3 multiply with the current there. Let me just put it as high here. So our high, to solve for high, I will then be equal to, there you have 16 multiplied by 3 divided by 4, and that will give basically 12.0 ampere. So to this question now, the very best option there is uh, option A. Option A is the right answer to that. Okay. So 38. In the diagram above, a 200-watt bulb is lighted by a 240 volts AC alternating current main supply. If 1 kilowatt hour is sold at 40 naira, the cost of keeping the bulb lighted for a day is, and you have the options there as usual. Similarly, this is also coming from current electricity, but just that it has involvement with cost. So it has involvement with cost. So first thing you need to know about cost is that it is dealing with power. So for question 38 now, 38, power is actually equal to IV, yes, which is same thing as QT. Rather, I mean Q over T. That is rate of flow of electricity. Q over T, right? So when you look at the question very well, let's say some of the parameters we have. Okay, we already have the, okay, a 200-watt bulb is lighted by 240 AC, means if 1 kilowatt hour is sold at 240 naira, the cost of keeping the bulb lighted. Okay, I don't know if we are giving time. Okay, for a day. Oh, okay. We are giving time a day. Time is equals to 1 day, right? And my bad, you need to know the, yes, what you need to be particular with is the quantity of electricity that is supplied to the by the mains, which is Q. So from here, you agree with me that Q, capital letter Q, is equals to PT. That's power multiplied with time. And obviously, you expect the unit here to be kilowatt hour. That is if you maintain your power in kilowatts and your time in hours. So which means that this given time, you need to convert it to hour. 1 day is made up of 24 hours, right? So 24 hours there. And the power given, I said 200 watts, yes. So you have 200 watts given there. So P is equals to 200 watts. 200 watts. So let us quickly calculate the quantity of electricity that will be consumed. So Q is equals to PT, which is equals to P is 200 multiplied with 24 hours. So you're going to have that to be equals to 4,800. This will be watt, yes, hour, because the unit of my power that I used there was in watt, and the unit of my time here was in hour. So let's convert this quickly to kilowatt hour. I'll just simply divide by 1,000, right? Or I just do times 1 kilowatt, which is made up of 1,000 watts. That's the conversion. So Watt is going to cancel out watt. 1,000 will go out of 4,800. You're going to have 4.8, and the kilowatt remains there. So kilowatt hour. Now the question says that based on the cost, it says if 1 kilowatt hour is sold at 14 naira. So that's it. Like you want to do something like a proportion here now. So meaning that if 1 kilowatt hour is already equals to 40 naira, 40 naira, then what do we think this 4.8 kilowatt hour will be? You can probably make that x, right? So you want to solve for x now. How do we solve for x? Because multiply. So that means x multiplied with 1 is equals to 40 multiplied with 4.8. So eventually our x, the unit must be in error, yes. So when you multiply 40 with 4.8, you have 192 naira 0 kobo. So to that, you're gonna have 192 naira 0 kobo. You have option A as the best answer there. 39. A power supply is transmitted at a very high voltage and low current in order to, yes, at a very high voltage and low current, power is transmitted so as to reduce the effect of overheating. Overheating actually is the reason why power is being supplied at very high voltage and low current. Heating within the wires or the cables or the coils is due to the effect of electric current mostly. Yes, electric current is the main cause of heating of cables, wires, or coils, or whatever it is. So to this now, gonna be choosing option B. So that means prevent overheating of the coil. Also, we're going now to question 40. In the diagram above, if the south poles of two magnets struck a steel bar, the polarities at T and V will respectively be. So here you have magnets. This is a steel bar here. This is a steel bar. So the magnets are used to stroke this steel bar at this point U, as you can see here, at this point U. So you must note that as we are using this particular magnet to stroke the steel bar at this point U, there will be at the opposite end. The opposite end is going to take an opposite polarity. So meaning at this point here, you expect not here, and also at this point here, you expect not to be here too. So they're gonna take opposite polarity due to stroking. That is stroking by double touch method or so. So if you have those sides to be not, then you expect the answer to be option C, right? 41. A galvanometer with full scale deflection of 10 milliampere, yes, is to be converted to voltmeter with a full deflection 5 volts. So that means that the voltage that is stated that way, that the voltage of the voltmeter is 5 volts, but the current of the galvanometer is 10 ampere. So I'm going to say current of the galvanometer, that is 10 milliampere rather. Voltage of the voltmeter, just ordinary V, that is 5 volts. If a series resistor of 498 ohms is used for the conversion, so a series resistance is connected. So that means that the resistance that is connected in series, let's say series, yes, you need to know the area of this question. You know, as far as galvanometer is concerned, with conversion, we have shunt and we also have multipliers. So shunt, you also need to know how they are being connected. Shunt is connected in parallel, and it's it's when you want to convert a a low current to high current, right? Because shunt itself is a low resistance uh, wire that is connected in parallel. Why? For series, you use a multiplier, which you want to use to reduce a current. Probably you have a high current before, so you want to convert it to a low current. So you use multiplier, and it is to be converted in series. And please know that this multiplier is of high resistance, but it is connected in what? In series. So when you have high resistance, of course, it's going to oppose a greater amount of current passing through. So definitely for this one to be connected in series here, is definitely going to be a multiplier. So let me say resistance of the multiplier, that is 498 ohms. Okay. So you want to look for resistance of the galvanometer. So let's go to that quickly. Okay. So since they are connected in series, please, for every series connection, any series connection, for any series connection, you need to take note that something must be constant in a series connection. But for a parallel connection, something is also constant as well. So for a series connection, what is constant is that same current is going to flow. Same current is going to flow, right? Same current flows while there are different voltages. This will have its own voltage, let's say voltage 1, and this will have its own voltage as well, voltage 2. So let me say if this is the galvanometer here, sorry, it's meant to be a circle. Actually, let's have it this way. It's meant to be a circle. It is deflection inside. Let's put it that way. So that's galvanometer. It's going to have its own voltage. It's also going to have its own resistance. Same current flows. V2, that is multiplier there. So I'm going to take this as the multiplier. It's going to have its own voltage. Also going to have its own resistance. So let me say resistance there, resistance M, resistance there, resistance G. So we know that for this galvanometer, using the Ohm's law, VI, or let me say VG, since it is galvanometer, not to cause confusion here. So VG is equal to IG multiplied by RG, right? Why this VM is equal to current of the multiplier multiplied with the RM. Since I said in a series connection, same current flows, so simply implies that this, whether it is IG is equals to IM, they'll be same, equals to the total I, right? Equals to the total I. But it is the voltage that will, so I don't think, let me check if they give us total voltage there. Okay, to be converted to a voltmeter with a full scale deflection of 5 volts. Okay, we are rather given what the voltmeter is to be measured. Okay, so that means that please know that V total must be equal to voltage of the galvanometer VG plus voltage of the multiplier. So when it says that to convert to a voltmeter with a voltage of 5 volts, so that means that is what we want to measure at the end of the day. So that's why I'm saying V total there. So my V total is the 5 that we're given, the 5 volts equals to VG. You know that is IG, RG, but I is same for both. So I'm going to do this plus IM. So that is I, which is also same for both, RM. So that is 5 is equals to, you can factorize out I, have RG plus RM there. So we're going to solve for, don't forget, we want to solve for resistance of the galvanometer. Resistance of galvanometer is what we're looking for. So from here, I can say that 5 divided by the given flowing current is equals to Rg plus Rm, which obviously from here you can arrive that Rg, which is the resistance of the galvanometer that we're looking for, is equals to 5 divided by the given flowing current minus resistance of the multiplier that is connected in series. So what is the given current in that is flowing all together? That is 10 milliampere. So you're giving your current to be 10 milliampere. See, all these conversion are necessary, so you need to convert. This milli is the prefix here, so that is 10 exponential negative 3 ampere, and that is 0.01 ampere. And you have resistance of the multiplier, that is 498 ohms, right? 498 ohms. So let's please solve for that. So Rg equals to 5 divided by uh, 10 to 0.01, that's 10 to the power of negative 2 minus 498, which is equals to, this is 500 minus 498. So of course we expect Rg to be equals to 2 ohms. So expect that to be 2 ohms. So to this question now, it's going to be question, it's going to be answer A. Now, if you were probably given shunt, if you were given shunt, it will be a parallel connection, and you know how parallel connection can look like. It's going to be something like this. Not actually a very perfect diagram, but to just depict what you might think of it there. So this should actually be the galvanometer showing the full scale deflection or deflection of the of this when electricity flow. So this is the shunt. Please do not forget that shunt is a low resistance wire. Shunt is a low resistance wire, please, connected, is a very common UCM question, connected in parallel, as we see in the diagram. But as for multiplier, we're going to say a high resistance wire connected in series. So you need to take note of that, please. So for shunt, this is the diagram for that. So when we eventually see a question along this way, we're going to treat that. So 42 rather. Two inductors of inductances 5 millihenry and 15 millihenry are connected in series, and the current 5 ampere flows through them. The total energy stored in the inductors is, so this is coming from inductors. So you need to know that energy stored in an inductor is equals to half Li square. So the L is actually the total inductances. So here you just sum up the inductance together. So my L inductance will be addition of those two. That's 5 millihenry plus 15 millihenry. I have 20 millihenry there, which is equal to 0.02 Henry, right? So what will I do to that now? And then I use the formula to get my energy that is being stored. So to get the energy, E, remember I said E is equal to half Li square, which is equal to half multiplied with, so I have 0.02 there for the total inductances when we sum up together. 0.02 multiplied with the current 5 square. So multiply 5 square. So you're simply going to have that to be 0.25 joules. Okay, 0.25 I have, but I'm having 250 joules here. Maybe the the given inductors are not actually having the prefix milli. So I will assume you're supposed to have this as a answer. Okay. So for 3, in the alternating circuit at resonance, the angle of lead or lag is, so this is coming from simple AC circuit. So as far as simple AC circuit is concerned, is about lead or lag angle. Okay, first you need to know the formulas for uh, inductive reactance, XL, that is omega L, which is equals to 2 pi FL. Capacitive reactance, that is 1 over omega C, which is equals to 1 over 2 pi FC. So, you need to know those ones. So, you need to know that in a capacitor, voltage lags by current leads. By what angle? I'll be by pi over 2 rad, or equivalent to 90 degrees, because uh, the capacitor is actually something that makes use of voltage in its energy formula. As you can see, you know that energy formula for capacitor is E. E is equal to half CV square. So just because you have voltage involved here tells you that it's going to suck in, or it's going to take in some voltages. So you expect the voltage in there to be reduced. So that is why it will lag, while the current will lead, and by this phase angle 90 or pi over 2. While in an inductor, you expect voltage to lead, while current lags. Same reason that applies for the one above there is also the fact that the energy formula for inductor is E is equals to half Li squared. So just because you have current involved here in the, as part of the formula of the energy that will be stored by the inductor, so you expect the inductor to take in or to suck in some current such that the voltage is not going to gain a head or have an edge over the current. So also by this same phase angle, pi over 2 in radians, please, or 90 degrees, then converted to degrees. So, and do not forget in all this impedance, which is the uh, overall reactance, or overall opposition to the flow of current, which depending on the combinations that you have in the circuit actually, but you can have this for the actual formula there. Okay, so quickly now, so it's saying that at resonance, yes. So please, you need to note that at resonance they do not lag or lead, because at resonance you're going to have the capacitive reactance at resonance, you're going to have the capacitive reactance equals the inductive reactance. So you're going to have that. So meaning that you're going to have XL is equals to XC, or XC is equals to XL. Okay. And yes, how do we actually calculate for phase angle? So phase angle is actually calculated. Uh, this is a kind of a diagram for the phase angle and how it's being obtained. On this axis we have XL, on this axis we have XC, but at this junction you have the subtraction of both. So I can have the equivalent at this middle point. Right? At this point is where you have your resistor. So a line drawn out here goes up there, and then here you have the angle there. So there you have the angle. So if you trace this down here, you're gonna have this side also to be equivalent to XL minus XC, right? Yes. So by simple mathematics, this side is opposite, this side is adjacent, and this side is hypotenuse, right? So this hypotenuse side is actually the what? Yes, you're gonna have, using Pythagoras square, hypotenuse square is equals to opposite square, that's XL minus XC square plus adjacent square, R square. So your hypotenuse square, or the hypotenuse rather, will then be equals to the square root of XL minus XC square plus R square. So eventually, it happens to be that this, your hypotenuse, is actually the impedance, okay? It's actually the impedance. C square R square. So to kind of get this phase angle, you can use any of those, but let's use this cos theta as the case may be here. You're going to have cos theta is equals to car, right? Adjacent divided by hypotenuse, so that's over R over Z. So if at resonance, capacitive reactance is equals to inductive reactance, it's something that you have XL equals to XC. So when you substitute that into this equation here, you're gonna eventually have that your value for Z at that same resonance, value for Z will now tends to be equals to R square plus, if XL is equals to XC, so you're going to have Z square there. Eventually your Z is equals to R. So meaning that at resonance, overall opposition to the flow of current is actually the opposition offered by the resistor, which is the resistance. Okay, so let's just quickly get the phase difference at that resonance, cos theta, which is equal to R over Z. So if that is the case, at resonance you're going to have cos theta is equal to R over Z. At resonance, Z is equal to R, so equals to 1. So to get the theta, theta is equals to sine angle of 1. You're going to have this to be equals to 0 degree. 0 degree. So that is at resonance. So you need to take note of that. It's very quite common. So I'll go with option B then. 44. In Faraday's law of electrolysis, the graph of mass deposited against the quantity of electricity is plotted. Okay, so the slope of the graph shows. So when it comes to electrolysis, this is coming from electrolysis. So you're going to have for electrolysis, there are two laws for electrolysis: the Faraday's first law and Faraday's second law of electrolysis, right? So mass deposited, the first law, quickly. First law, you have mass deposited is directly proportional to the point of electricity that is passing through the solution of the electrolyte. So you have M against Q, such that when you remove this proportionality sign, you have M is equal to ZQ. So it happens to be that when you take the slope, it gives you electrochemical equivalence, M over Q. So electrochemical equivalence is the slope equals to M over Q, which is equal to the electrochemical equivalence, right? That's the first law. The second law for different solutions of electrolyte, which you're gonna have that the number of moles of each of the uh, metal ions deposited or liberated at the solutions of the electrolyte is inverse proportional to the charge on their respective on the respective ions actually. So N is inverse proportional to C. So what is constant here is that the quantity of the electricity is constant in Faraday. So N is equals to quantity of electricity in Faraday is constant divided by C. So you have quantity of electricity in Faraday to be equals to NC. So to convert this to Coulomb back, because it's in Faraday, quantity of electricity back in Coulomb, you need to multiply through by the Faraday's constant. Yes. And do not forget the value of the Faraday constant, F equals 96,500 Coulomb per mole. So Coulomb per mole. So that is a quick one there. So the question there, the slope will give the uh, electrochemical equivalence. 45. In a discharge tube, most of the gas is pumped out so that electricity is conducted at. So you just remember that it is in the discharge tube we work with low pressure and high voltage. Low pressure and high voltage. Low pressure and high voltage. So what do you expect the answer to be here? I have two high pressures. So definitely that must be most likely an error. So you expect one of these options to be low pressure. So whichever one that is there, so it is what we're going to take. So this should be low pressure actually. So let me probably run this for low pressure. So if I run that for low pressure, I'll take that as my answer for this question. Option B. I'm taking option B. So I'm taking option B here for low pressure and high voltage. Low pressure and high voltage. Option D is just low voltage, so that's not right. 46. The radioisotope uranium-235 of atomic number 92 decays by emitting 2 alpha particles, 3 beta particles, and a gamma ray. What is the mass and atomic number of the resulting daughter element? So you have decaying of uranium-235. Uranium-235 is decaying and releasing some important materials or some important radiations. So by emitting 2 alpha particles, 3 beta particles, let's say this is the supposing daughter element that is released, let's say of mass number X and atomic number Y. So releasing 2 alpha particles. 2 alpha particles. Alpha particle is having 2, 4. 3 beta particles. Beta particle, the most common one is the negatron, which is negative 1, and a gamma. So a gamma is just 0, 0, right? 0, 0. So this question here, what is the mass and the atomic number? So you know that gamma ray do not actually contribute to the change, any change whatsoever in both the mass number and the atomic number. So what we focus on here is the alpha particle and the beta particle. What we want to do when it comes to nuclear reactions is that you want to make sure that the total mass number on the left hand side of the equation as on the reactant side should be equal to what you have on the product side. So I'll say 235 is equals to, I'm going to sum up this x. I'm going to multiply 2 by 4. I'm going to multiply 3 by 0. And this is plus 0, right? So this is equals to x plus 2 times 4, that is 8. Or let me show that so that there will be confusion anyway. 2 multiplied with 4 plus 3 multiplied with 0 plus 0. Give that 235 is equals to x plus 8 plus 0. So x is equals to 235 minus 8. So this is equals to 227. Now let's solve for y. Also, the atomic number there must be equals to this, is equals to this times this, is equals to this times this. So you're going to have 92 is equals to y plus 2 times 2 plus 2 multiplied with negative 1, then plus 0. So this is 92 is equals to y plus 4 minus 3 plus 0, right? So this eventually gives you that y is equal to 92 minus 1, which is equal to 91. So your x comma y, as the case may be here, x is what? X is 227, y is 91. So 27, 91. So you have this quickly. 47. The ground state energy for a hydrogen atom is 5.44 times 10 to the power minus 19 joules. If an electron jumps from 0 to ground state, calculate the frequency of the emitted radiation. So this is coming from emission of radiation, right? That's uh, atoms, right? Atoms, emission of radiation. So the energy involved there will be given 5.44 times 10 to the power minus 19 joules minus 19 joule. You already have your H there, which is 6.6 stress per negative 34 joule seconds. So it's asking for what is the frequency. So that you simply gonna use this equation. E is equals to HF. So you use the formula here. Uh, E is equals to HF. You have 5.44 exponential negative 19 is equals to 6.6 exponential negative 34 times F. So you're simply going to have that F is equals to 5.44 negative 19 divided by 6.6 that's by negative 34. So this should give you 8.24 steps per 12 at. Oh, do we have any ground states the electric drops from those, calculate the frequency of the emitter to, so E equals HF, H is 6.6. Do you have any error there? Okay, probably error from their end, not sure. I'll check that later. Okay, okay. So 48 transistors are used for the so basically you need to know the use of transistors. So amplification of signals. So think of that. 49, a typical transistor characteristic is represented as, yes, so this is the IV diagram relationship. So you expect the answer there to be uh, this exponential rise, exponential increase in both the current and the voltage. So, and 50, which of the following is a pure semiconductor. So a pure semiconductor, you expect that to be silicon, right? Silicon. So that will be the end for this series. So we'll meet the next one. Thank you so much.